Okay, year 11, day one, back on the job and my voice is toast. That is your fault, but I'll do my best. Here is the video as promised. And you may be asking yourselves as you look at the screen, what on earth is this? Well, I would have thought it's obvious. It is a potato. And we will be experimenting on those tomorrow. So this video serves as a little preparation so that we get the maximum amount of practical time and you don't have to waste the lesson listening to me give instructions. Okay, so this is our osmosis practical. This potato is what we're going to be working on, but obviously we're going to need a sample of the tissue. So what you will be doing is you will be using a cork borer to very carefully remove a cylinder of potato tissue. Now, of course, potato tissue, we know it is a plant, so that cylinder will be made out of cells. And here's a cell I prepared earlier. Okay, so here's our plant cell, and what I want to know when we do this experiment is exactly how concentrated is the stuff inside the cytoplasm. So here's our plant cell, that's the nucleus I've got an arrow pointing to. The cytoplasm is, of course, this bit here, and inside there will be some water molecules for sure. We'll have quite a few of those floating around. But there'll be lots of other stuff. There'll be sugars, there will be a few proteins, there will be some glucose, and my question is, how would we work out exactly how concentrated it is? I want to know what is the amount, if you like, what is the molarity or the concentration of the sugar in there, and we're going to do an experiment to work that out. Okay, so this is what we're looking at, the cytoplasm in particular, and we're going to be comparing that to some stock solutions that we make up. So here's how the method works. You're going to take your sample of plant tissue and you're going to put it in different solutions. We're going to draw what we might expect to see on this page here. Now in our first one, let's imagine we put it into a solution which has got loads, absolutely tons of glucose. Okay, so let's put lots of glucose. Let's get that arrow in here actually. Let's put tons and tons of glucose around it. Okay. Now the glucose is dissolved in water, so we will need a few water molecules for sure. But what we're likely to find is that that glucose takes up most of the space in this solution, and there isn't very much room for water molecules around it. That means that there are likely to be more water molecules on the inside of our plant cell. Now this type of solution that we've put in out here has a name. It is more concentrated because it's got more glucose, so we call it high per. Per is important. Tonic. It simply means more concentrated, and we're referring to the glucose. There is more glucose on the outside of the cell than on the inside. There'll be a little bit inside, but not very much. Now what that means is that the water is going to be more numerous on the inside of the cell. So the overall movement by osmosis is going to tend to be outwards. Water is going to escape from that cell through the partially permeable membrane, and it's going to move out into the hypertonic solution. So this cell we might expect to shrivel, and overall our potato chip, which started off looking like this, well, it might end up looking a little bit like this. It's going to shrivel, it's going to lose mass. Okay, so that's a hypertonic solution. But there is, of course, the opposite example that we could explore. And that's this one down here that I'm going to set up. Now this one, we're going to put this particular plant cell into a solution that is mostly water. In fact, there'll be barely any glucose at all in this. So there's going to be absolutely tons of water molecules out there surrounding our cell. And our cell, as we've said, will have a little bit of glucose and other stuff in there, meaning that the water molecules on the inside are going to be less numerous. The sugar is going to be more concentrated on the inside of this cell than it is on the outside, where we've barely got any sugar. So overall, we would expect to see a net movement of water inwards. Okay, so the water is going to move in through the partially permeable membrane. Now this type of solution has a fancy name as well. It is called hypotonic. This is a hypotonic glucose solution because it hasn't got as much glucose in as the inside of the cell. So when you put those cells in a hypotonic solution, they're going to swell up, they're going to take on water, and we're going to find that our potato chip that started off looking like this may end up looking a little bit like this. Maybe I exaggerate that. But the main thing is that it gains mass. Okay, so far so good. Nice and straightforward. But this next bit is the tricky part. What we're going to do as a class is we're going to test lots of different strengths of solution. We're going to have some people testing really, really sugary water, and some people testing not very sugary water, and some people are already testing pure water. What we are going to be looking at is the effect this has on mass overall, because in some cases we're going to expect mass to increase, but in some cases we're going to expect the mass to decrease. So I'm going to set my axes up like this so that we can have a mass change axis over here. And this axis here is the concentration. Okay. And that's in moles, for those of you who remember your chemistry. Well, what we should find as that solution gets more and more concentrated, there's more and more sugar surrounding the plant, we should find that it loses more and more mass. So when the water is pure, we might find that it gains mass. When it's really concentrated, we might find that it loses mass. And there'll probably be some data points in between. Okay? What we are aiming to do, and this is the really tricky part of this experiment, we are looking for this magical point right here. At that concentration, no water is being either gained or lost. Overall, the potato stays the same mass. That means that this concentration must be exactly the same concentration as in our potato cytoplasm. So that's what we're looking for. This value that I've just highlighted is going to be equal to the concentration of the cytoplasm here. Okay, that's the instruction. There'll be more details to follow.